Price tables are like this. You have a reaction. Let's say you have two. Let's say you have this reaction. 2XO3. So generally you put that at the top, and you have initial concentration row here, change row next, and then an equilibrium concentration. But let's focus just for a second on this. So you have a column for each one of these. A column for this, a column for this, a column for this. But let me focus just for a second on change. All right. Any problem you get, there's at least one of these that you know the change. Well, let me initiate it this way. If I said the change here for the oxygen is plus X. So this is where you introduce the variables for these types of questions. All right. If that's plus X, that means we're flowing this way and increasing this. If that's plus X, and remember there's basically a 1 there. If that's plus X, this is going to be plus 2X because of that 2. You with me? This has a 2 as well, but the X I'm going to put here is going to be negative because it's flowing that way. So negative 2X. So being able to do that is one part of doing these ice tables. All right, I've just got a few examples here to go through. Here's the blue eraser. What if you had four NH3 plus 2 plus all right, so watch this one. If I say this one is plus X, since there's a 3 there, this one is going to be 4/3 X plus 4/3 X plus X. These are going to be minus. Because of this 3, if that one goes up plus 1x, then this one goes up 1 1/3 x. This one goes up 2 1/3 x. And this one goes up 6/3 x. You could put a 2 here as well, just because of the way fractions work. So since this is a 3, I had to put this 4 over a 3, I put this 2 over a 3, and I put this 6 over a 3. You okay with that? CO4. If I do this one, I'll go plus x there. I've got a 2 here, so this one will be, well, let me do this one. We're on this side of the sign, the arrows. This one was plus, so this one will be plus 3x. And since this was on this side, it'll be minus 2x. You guys follow that? Plus 4CO. There's the arrow. And what if I did it? That's plus x. What is this going to be? Huh? Minus 4. It's, so here's the plus symbol, and here's the arrows. So this is going to be positive or negative. Will be positive. If this one's positive and it's on the left side, that means we're going this way, so this one's positive too. And what's the coefficient here? This one was 4. This one's going to be 1 over 4. You with me? And this one's just going to be negative 1. Since this says 4 and I just put x here, that means we have to put a 4 underneath this one and a 4 underneath this one. You guys follow this? I won't go through all of those. So let's do one of these. So generally for ice tables, you're trying to associate initial concentrations and final concentrations. And there's also the K value for whatever equilibrium you're talking about. This is actually exercise 13.7. This one is on 2 aqueous plus I negative aqueous aqueous. And here's what you're given for this one. You're told initial concentrations for these two so 1 times 10 to the negative 3. You're also told this one is 1 times 10 to the negative 3. So these are things you're given. You're also told at equilibrium, this one is 6.61 times 10 to the negative 4. And those are molarities. I haven't written the ends. All right, and then the question is, I think this one's asking for equilibrium constant K. And of course, Kc equals concentration of I, concentration of this over concentration of I2, concentration of I negative. Okay, so what is the Kc here? What we need here, we need these concentrations at equilibrium. So it's these things that we're looking for. All right. Both equal to this before reaction. they should state a little more clearly for these that this starts at 0. Generally, when you do an ice table, you want one of these to start at 0. All right, so if we start at 0, now we have to figure out what the changes are. So the reactant is 0, the product is 0. Here's my reactants. So is this going to be positive or negative? This is going to be negative? No. If there's none of this, and you start with these, it's necessarily, because this is an equilibrium, so if there's nothing over here, it's going to have to go this way. You see what I'm saying? So this is the one that's positive, and the other two are negative. And I'm just going to say plus x. I'm going to say this is minus x, and this is minus x, because these are all one-to-one relationships. So there's my changes, my x's. When you have a full column like this, you can go, all right, I start at, that was my starting concentration. I went minus x to get to 6.61 10 to the negative 4. So you could solve for x here, but let's do this. And maybe this was obvious from the beginning. But these two started at the same value. They're both minus x. This one ended up 6.61 times 10 to the negative 4. So we know necessarily that that next one is 6.61. That one must necessarily be true. So there's one that we weren't given. All right, if we solve this for x, then we can solve the rest of this. What do I want to do here? Three minus 6.61 times 10 to the negative 4 minus x equals 0. Algebra-wise, now I'm just going to add plus x to both sides. So solve for x with algebra. But I'm just going to use what they already have here. But this minus this gives us 3.39. X is 3.39. So if you do this, you get 3.39 times 10 to the negative 4. That is x. So I used this column to solve for x. This column I used to solve for x. Now that I have x, I can solve everything else. I could have said, now that I have this, I can solve this, but that's what that's going to be. This is going to be see what I did to get there? Right. Now that I have everything in this row, I can solve for KC. You plug everything in there. You'll have that over these concentrations, 6.61 times 10 to the negative 4, 6.61. And then you can solve for KC. I guess this comes out to 776. So that's how you use the ice table to solve for KC. And again, note, we had some initial concentrations and some final concentrations. Usually when you have that, you're dealing with an ice table. Initial concentrations, final concentrations. This one. So let me do another one. This one. This is an acid base. So we started with equilibrium, then we went to the acid base chapter and we had dissociation constants but it would still set up the same way we do equilibrium. We're also going to do one more thing for solubility. It's called the solubility product. So, I mean, we had Kc, and we also had Kp when you base it on partial pressures for just general problems. And then we had Ka and Kb. And Kw showed up a little bit in our acid base. And we're going to get to something called Ksp. For solubility of ionic compounds. So they're all very similar, but now I'm going to go to the acid-base chapter and do an acid-base thing. So if you have, this is the reaction, HCN, aqueous, H plus, aqueous, Cn minus, aqueous. You're told you have so you're told you have this solution. And we go initial change in equilibrium. And we also have we're still doing this as a concentration. Equals. So we're saying we got this out of a bottle, and let's say we had 1 liter of solution. We put 0.15 moles of this into the solution. 1.5 moles of this was put into the solution. It does this once it goes into the solution, but the 0.5 moles came out of a jar dry, was weighed on a scale such that it was 0.15 moles, and was put into our 1 liter. So what would you put down for initial concentration of this? You weigh it out on a scale. It's 0.15 moles that you weighed out on the scale. You dump it in, and let's say just before it hits the water, you have this many moles. You have basically, let's say it all goes into the water, but time freezes for a second, and this doesn't happen. It all just flops down into the water. So what's the initial concentration here? It is 0.15. And this is 0, this is 0, before it starts to dissociate into the ion. Does that make sense? It's usually stated this way in a problem. I have this molarity of HCN solution, but you know that it does this in the solution. So those are our initial concentrations. So what's the change going to be here? What's the X? It's going that way. So positive or negative? It is negative. We're just going to say negative X. These are all ones, so negative X plus X plus X. What are the concentrations of equilibrium? Concentrations. And also for this one, we're given, you couldn't do this unless you were given those. So we're given that. So we need to solve for these and then set them equal to that. So what we're going to do is this one is 0.15 minus whatever x is. All right, now that we have this whole column, we can go, well, let's just bring this one down. 0 plus x is x. 0 plus x is x. And now we're going to look at this. All right. Concentration for the H plus is x. Concentration for the Cn is x. Concentration for the HCN is 0.15 minus x. And of course that all equals 4.9 times 10 to the negative 10. So now we can solve for x. But notice this is a kind of an awesome trick that helps you a lot. We're stuck with, well, let me do this first. This is x squared. I'm going to put x squared here. All right, now I'm going to take this and move it over to the left side by multiplying both sides by this. So 4.9 times 10 to the negative 10. Okay, so I just multiply both sides by this. Now I'm going to do this multiplication. It's going to be this times the 0.15 and then this times the x. I'm just going to repeat to see what that comes out to be. So the 4.9 times 10 to the negative 10. Make sure I'm getting the right one. 0.15. I don't know why I'm questioning this. Times 4.9. Yeah, 7.35. Okay. So that's going to be that times that. 0.735 times 10 to the negative 10. Yes. Okay. So these two times each other is this. And then there's a negative sign there, so it's negative. You guys see what I did? I know the powers of 10 screws you up. So 0.15 times 4.5 times 10 to the negative 10 is this. And then we have 4.9 times 10 to the negative 10 x equals x squared. You see what I did? Power of 10 is making it look complicated. All right. Now I'm going to move everything over to the left side. So x squared minus 7.35 times 10 to the negative 11 minus 4.9 times 10 to the negative 10x. So this I'm working on it equals 0. But let me rearrange it as x squared minus 4.9 x 10 to the negative 10 minus what I'm trying to say here is x is what we have is quadratic equation that you could solve with the quadratic formula to find x. Some of these, I haven't put any on D2L where you have to do that yet. But let me back way up just to show you there's a way we can avoid, and this will make you very happy, the quadratic formula. When we were here, this was the KC we were given. We had it set up like this. If KC, I would say like 10 to the negative 4, or 10 to the negative 5, 10 to the negative 6, anything that's this small, you can assume this x is negligible. Meaning you can pretend it's not there, which makes this a lot easier to solve. See what I'm saying? You assume this x is really, really small compared to the 0.15.
Have you decided to do x squared again? That's on top.
This was x, and this was x.
Okay.
So that's where I got the x squared. X and x. And this was 15 minus 0.15 minus x is what it is. So we're just going to get rid of that x. And I have some of those on D2L to solve. And it says in there, assume the change is small enough that it's negligible. So you know that you can ignore it. And then that simplifies this a lot. So now I'm going to go get rid of that. And now it's just 0.15 times 4.9, which was so 0.15 times this is 7.35 times 10 to the negative 11. So I just multiply both sides by this. So I get that on the left side, and this is what's left on the right side, and now you can just take the square root. You see what I'm saying? For this one, the square root. Rearrange, do the quadratic. No, we get 6. This is what it's been done for. So this was asking for all the concentrations. So I guess we're not really done. Value of x calculated is d2. Okay. I erased everything. So if that's x, we have so I had this for the equilibrium concentration for HCN, and then so this is the concentration of these two. And then to find the concentration of this, we could do that. To find it. Right. Let's do one. This one is an actual weak acid. So we'll have a Ka. What is the here we have Ka 1.8 times 10 to the negative 4. And our equilibrium, this is 14.12. Here's what we've got. We've got this as our acid, H2O liquid makes H3O plus aqueous plus CO2H. Do it this way. HCO2 minus this. CO2 minus aqueous. So we've got 4 columns here. And then they tell us we start with this molarity solution of HCO2. For our Ka value, we ignore this because it's liquid. So our Ka is still in the coefficients and concentration. So we're leaving this out. So really our columns are just this one, this one, and this one. All right, for initial concentration, what's the initial concentration here? This one. We have a 0.534 molar solution. So it's this, and we assume this starts at 0 and this starts at 0. Our change, these are all ones, 1 to 1 to 1, so we're going to say, is this change going to be positive or negative? Minus x, and these two are going to be positive x, and then the equilibrium of the concentrations. We've got our Ka. We know that this is going to be 0.534 minus x. This one is 0 plus x, so it's x, 0 plus x, this is x. And just like before, that's x, and this is 0.534 minus x. Equals 1.8 times 10 to the negative 4. And we're going to do it again. We're going to assume that this x can be ignored because this is so small compared to 0.534. And it is an approximation, but it's good out to a few significant figures. So really what we're solving is (1.8 times 10 to the negative 4). You multiply both sides by this, and what will you get? That times that is 9.6. And then you just find the square root. Equals the square root of that is, turns out to be 9.8 times 10 to the negative 3. This is asking for the concentration of H3O plus. And H3O plus was just X, 0, and then we had plus X, so it's just X. So that's the concentration of H3O plus. I didn't put pH on test 2, I don't know why. I'll put pH on test 3. But you could go from the concentration of H3O plus I guess I didn't put it on here. So you could directly find H3O plus once you find the concentration. You could directly find pH once you find the concentration of H3O plus by doing that. So I have stuff like that on D2L. Yes, I did. Make a new category. These stuff. So there you go. There's a few of these that you can practice. I think I'll have 3 of them, but you can practice these the way I just did those. Let me do this one. This is AC. What is the equilibrium concentrations? This one KC is 1.07 times 10 raised to 5. That's your equilibrium. This one says there's 1 liter of solution, and there's 0.129 moles of N2O4 in it. But that's the definition of molarity. If you've got 0.129 moles in 1 liter, solution, we can write that as 0.129. So this is just saying I don't think I phrased the ones I put on there that way. I just went ahead and said 0.129 molar. This is number 74, chapter 4. 14. All right, so if we do this one with the ice table tray, we're starting with this molarity of N2O2. So initial concentrations, this one's going to be 0.129. This one will start at 0. Change, is this positive or negative? So minus x, and this one's going to be plus 2x because of that 2. You with me? The 2x. Set all the information to give me this. And we've got the KC over there. All right. At equilibrium, the concentration is 0.129 minus x. This one is 2x. So we can write this squared. Don't forget this square because of this. Equals 1.07 times 10 to the negative 5. You guys with me? And then I'm going to do 2x squared for the N2O2. Because this one's concentration is 2x, but we've got a squared that goes with it. And then this one is x. And this one says explicitly you can assume this x is negligible. So now you've got this is going to be 4x squared. Going to make that negligible. And then you just solve from there. Multiply both sides by this, then divide both sides by 4, and then find the square root. And that one, well, I didn't write the answer down to this one. That one's in the book, though. You can look up the answer to that. So I have some of those. Yeah, those are the ones I just wrote. Now we're going to talk about something called the KC, KSP. SP just means solubility product. But it's the same idea that we've been working on before. We build our equation the same way. But we're talking about this now. Let's say I had CaF2, and I put it in some water. Have that as a solid. I put it in some water, and it breaks out into Ca2 plus 2F minus, and these are aqueous. Last semester, do you remember solubility? You had to learn, you had a little chart, all nitrates are soluble, sulfates are all soluble except if it's this and this and this. Okay. What we mean by soluble, a little more specifically what we mean by soluble is you can saturate a solution, like even something that's easily soluble, like NaCl. You can put NaCl, it all disappears. Put a little more NaCl and it all disappears. And you just keep doing that. Eventually, you reach the saturation limit, and then any more NaCl you put in there, it's just going to fall down to the bottom. It's still a crystal. We don't generally talk about that situation when we go over solubility in first semester. Second semester, there's that, but usually we deal with an equilibrium. So actually, that NaCl solution I was talking about, you end up with an equilibrium between the solid NaCl and the Na and Cl. Once you reach that saturation limit, any more that you put in is going to be in this equilibrium. Compounds that you would have said are insoluble last semester, the truth is they're all just a tiny, tiny bit soluble, but unless it's very easily soluble, we just say it's insoluble. Because if you put some in water, you're just going to see it. You're not going to notice that a little tiny bit of it dissolved. So even things that are just marginally soluble, we can still talk about this type of thing. Like you would have learned, you would have seen that on the chart, but let's see. I would say, is this soluble or not? You would look at the chart and you would look under chlorine and you would go, these are all soluble except, and this is one of the exceptions, so you would say that's insoluble. But the truth is, it does do this by just a little bit. And we would say the KSP of this is, it's something very tiny. It's times 10 to the negative something big. It's just this tiny, tiny, tiny amount does this. And that's kind of the condition we use to say that it's insoluble. If it only just a barely a little bit ever dissolves. So in this chapter, this is chapter 15. We're talking about things that are just marginally soluble, like PbCl. They all do this. They have this situation where they're slightly soluble. So I have this, and I say the KSP is this. Notice, for every one of these, this is going to be a solid. So we're just talking about one compound on this side. And then we talk about its solvating ions on this side. So our KSP is always going to be, for instance, KSP for this one is F minus squared because of this. And it's, since I'm not including this, is essentially a 1 there. So yeah, the KSP is actually just that. It's just this part. You see what I mean? So if we talk about solubility products, it's always like this. And that's why it's called a product, because there's not even any division. It's just this times this. So there's the definition of KSP. It really is, you get the K the same way we get any of the other Ks that we've done in the last 2 chapters. So that's what we're talking about in chapter 15. And we go on to the ice too. Guess I'll do this one first. Let's say you're given this, and let me get that KSP from. Is that the one from the previous problem? Yeah. Was it just there from the previous problem? We have this. You're told, this isn't an ice table problem. This is more easy than those. Concentration of calcium 2 plus equals, and that's again multiple. So you're told that, and you're asked, okay, if you did think about it as an ice table, you would say for every one of these, there's 2 of those. So if the concentration of calcium is this, then the concentration of fluoride is 2 times 2.15. See what I'm saying? This is what we're told. But you can use this to infer that the concentration of fluoride is 2 times whatever the concentration of C8 is. They don't use an ice table. Maybe it's instructive to write one. What if I did this? We don't know the initial, but the change would be this one. If we started with some amount of this, and then we ended up with plus x, you would say plus 2x here. And then this is saying that the equilibrium concentration, without doing any math, is this one's x is. So maybe that helps connect things, but 2 times x is what the concentration of this one is. So 2 times 2.15. So the point is, now you have both of these, and you can find KSP very easily. This is example 15.2. So this times this. So the KSP here is you would come up with negative. So that one's kind of simple. I think I put some of those on here. Did I? KSP for the equilibrium concentration. So let me put that. Stuff. Do this one too. This is what I'm about to do next. I really need more of these, but at least you have something to practice. I'm going to try to stay more caught up on these. Okay, the next thing I'm going to do involves ice table. This will be exercise 53. This is what we're putting in some water. It's marginally soluble, but it still does this by a little bit. And we're also told ASP for this dissolution process is 6.3 times 10 to the -9. Calculate all right. I haven't told you what the molar solubility is yet, but it'll be easier to just point at it if I start this. So we're going to start this the same way we did before. I'm going to do an ice table, and I'm going to go initial values. Some amount of this goes in there, but since the KSP doesn't involve that, since it's a solid, it only means Cu plus and Br minus. We're not really going to do anything with it, but let me call it, what's a variable I can use? I'm just going to say n, but we're really not going to do much with it. Okay, but let's say we put some of that in. This is 0, and this is 0. We're told the KSP. And in some sense, I could say, okay, we're trying to find the concentrations of these, so let's just kind of do that. So this is going to be plus x, this is going to be plus x, and this is going to be whatever it was to begin with minus x, because that's 1 to 1 to 1. All right, so that's the change, and then equilibrium, I'm really only involving 0 plus x is x, 0 plus x is x, and if I wanted to write this, I would just say, that just should have been minus x. Down here is where I would put n minus x. And maybe it's obvious where we're going, but equals 6.3 times 10 to the negative 9 equals, and it's just going to be x squared. So we can solve for x very easily. We're just going to take the square root of this. X equals 10 to the negative didn't show up correctly. So this was asking to calculate the molar solubility, I should say, of CuBr. But if it said find the equilibrium concentration of the copper ion, you could find it easily that way. And since these are the same, it's also the molar concentration of Br. So we're saying the molarity of this solution in copper ions is 7.9 times 10 to the negative 5 moles per liter. All right. What the molar solubility of CuBr is that. It's saying a tiny amount of this will actually dissolve. It's a tiny amount, but how much is it? It's this x. In this case, it happens to be what we calculated for these. But whatever amount of this original that dissolved, that's called the molar solubility. See what I'm saying? So it ends up being 7.9 times 10 to the negative 5 in this case, because these are all 1 to 1 to 1, so they're all related. So however much of this dissolves is called the molar solubility. I have some other examples here, but those are the ones I have in here. So I think I better do the second one. PBI is 2. Ag2SO4. Ag2SO4. So that's the compound. solve. AG2, AG2 plus 2AG2 plus equals plus 4, 2 minus. So I've got 2 here. You're given these for these types of problems. Let me look at one real quick. AG2 SO4, a bunch of these in the appendix. So it's over 1.2 times 10 to the negative 5. That's what we have. And in this case, KSP equals concentration of Ag plus squared times concentration of SO4 2 minus. There's that. All right. And what if I did, let me do this again. I'm just going to say n, and let's say initially that's 0 and that's 0. The change here is, if we start with this and it's going that way, this is going to be negative x minus 2x plus 2x and plus x, which means at equilibrium, the concentration will be n minus this x, this one will be 2x, and this one will be x. If this is KSP, we have 1.2 times 10 to the negative 5 equals the concentration of Ag. Notice it's squared, so I'm going to put 2x here, and don't miss this. It's 2x squared, so we're not done with 2's here. We're not done with this 2 just by putting 2x here. There's a square here too. And then 2x times x. So what's going to be on this side? Use your algebra skills with a z. What's that going to be? Can you not see it? Oh, sorry. Do this algebra. What are we going to have down here? 2x squared equals 4x squared. And then we still have one more x. So it's going to be 4x to the third. This is 4x to the third. You see that? Divide that by 4, and x to the third. I did check, these calculators will do that, the cubed root. I won't finish it just so you can, oh no, that's not one that was on mine, so I will finish it. 1.2 divided by 4. So that, and then I guess I would go 3.0 times 10 to the negative 6. Figured this out earlier. Clear. Alright, what I'm doing is, what am I doing? I hit inverse, I hit inverse and I hit this key. It's like that. Then I put in I can't do this my way, so I've got to do that. I've got to use these. 3.0. Isn't there a times 10 that there it is? 3.0 times 10. Six. I'm screwing this all up. I'm going to do that. I swear I did this upstairs. There it is. So now it says 3. I've got that. Now I want to put in 0.000003. 0.000003. That's what it gives me. So that's what X is. That's what X is. And that's what the molar, what do you call it, is? Molar solubility is. So anyway, learn how to do the cube roots or whatever roots on your calculator so you can solve these. And that's what I got for today. So that's the fun you guys get for coming to. That's free stuff. I've already got some stuff up there. So, ice tables are not that bad. And that's it. I'll have a good weekend. Try to get your stuff graded, your test graded Monday.